Hello. In my previous videos, we encountered the thermodynamic potentials and explained how these can be derived by considering the behaviour of a system in contact with a very large reservoir. This is elegant and better explains the physics that is going on in these situations. It is, however, conceptually difficult, so if you struggled with that video, it is perhaps worth learning a shortcut for the time being and coming back to that later when you don't have an exam to prepare for and are under fewer time pressures. The essence of this new method involves memorizing the following definitions for the various thermodynamic potentials that come about regularly in thermodynamics, as well as the combined statement of the first and second laws, dE equals TdS minus PdV. On this slide, we have definitions for the following thermodynamic potentials. The enthalpy H, which is defined as the internal energy E plus the pressure times the volume. The Helmholtz free energy F, which is defined as the internal energy E minus the temperature times the entropy S. The Gibbs free energy G, which is defined as the enthalpy H minus the temperature times the entropy S. And the grand potential omega, which is defined as shown at the bottom of this slide. The sum here runs over all the chemically distinct species that the system is composed of, and the mui's and ni's are the chemical potentials and numbers of atoms of each of these various components. Once you have memorized these definitions for the various thermodynamic potentials, you then need to know how to derive expressions for the infinitesimals. This is straightforward. Taking the entropy as our example, you simply use the product rule as shown here. You are thus left with dH equals dE plus PdV plus VdP. Obviously, we use the product rule in getting the second two terms here. You now substitute in the infinitesimal for the energy, dE equals TdS minus PdV. The terms in PdV cancel, and you are left with the infinitesimal for the enthalpy, dH equals TdS plus VdP. You can go through a similar procedure starting for each of the thermodynamic potentials shown on this slide. I will not go through that here and will instead leave it as an exercise. Another useful thing that you could do with these definitions of the infinitesimals is as follows. If we take dE, for example, we could write it in this way, that we have learned to write it by combining the first and second laws of thermodynamics, or we can write it as follows. The second result here, with the partial derivatives, is a well-known result in the theory of partial differential equations. In fact, it is just the fundamental theorem of calculus, in short, differentiation is the opposite of integration, but for partial derivatives. The nice thing is that we can equate the coefficients of each of the terms in these two expressions. We thus find that the various intensive quantities are all related to a partial derivative of the internal energy with respect to an extensive variable. We can do a similar trick with the infinitesimals that we obtain for our various thermodynamic potentials. Hence, for the entropy H, for example, we can write dH as either TdS plus VdP, or we can write it as partial H by partial S at constant P, ds plus partial H by partial P at constant S, dP. Again, we can equate the coefficients in these two expressions. If we play this game with all the various thermodynamic potentials, we thus find that all thermodynamic variables can be written as derivatives of thermodynamic potentials. We thus finally have a way of calculating the entropy. The entropy is the partial derivative of the free energy, Gibbs or Helmholtz, with respect to temperature. This derivative must be evaluated at constant P if we are looking at the Gibbs free energy, and at constant V if we are looking at the Helmholtz free energy. Once again, though, I will leave the derivation of these results as an exercise. This brings us nicely to the Maxwell relations that are the subject of this video. Remember that all our thermodynamic potentials are functions of state. A function of state is an exact differential, and for all exact differentials, the following result holds for their mixed second derivatives. The second partial derivative of our function e with respect to v and s is equal to the second partial derivative of our function e with respect to partial s and partial v. Let's consider what this means in the context of the results we have derived. From the logic on the previous slide, we know that the coefficients of ds and dv in these two expressions must be equal. By differentiating the first of these results with respect to v, we thus arrive at the following result. d2e by dv ds is equal to partial t by partial v at constant s. We can also arrive at a second result by differentiating the second equation with respect to s, as shown here. d2e by ds dv is equal to minus partial p by partial s at constant v. Now notice that the left-hand sides of these two equations are equal by the result that I stated is true for all exact differentials, or functions of state, in the top right-hand corner of this slide. If the left-hand sides of these two equations are equal, it thus stands to reason that the right-hand sides of these equations must also be equal. We thus arrive at the following result. Partial t by partial v at constant s is equal to minus partial p by partial s at constant v. The result that I have just arrived at is known as a Maxwell relation. Much as with everything else in this video, there are lots of different Maxwell relations, and we can again derive all of these results by starting from the various different thermodynamic potentials. Again though, I won't go through all that here because the methodology is the same. I will instead leave the derivation of all the Maxwell relations as an exercise for you to work through in your study time. Thank you for your attention.